as we move farther and farther out the x-axis, the y value of our function is essentially getting sucked into the x-axis. Our y values are getting tinier and tinier and tinier. Our y values, well, the y value is equal to 0 infinitely many times. So our graph is crossing our horizontal asymptote infinitely many times, and that's totally okay, as long as our y values keep getting closer and closer. So you tell me how far I'm allowed to, the largest y value I can find, and I'll tell you how far out on the x-axis we need to go so that from there on the y value stays less than that. Okay, that's how our horizontal asymptote works.
You just have like a regular sine wave, that one not exist then?
That's a good question. And so with our regular sine wave, we have the limit as x approaches infinity of sine x. Well, because the sine function oscillates up and down and never dampens, it just continues to bounce back and forth between, that's not the sine function, there we go. So with the sine function, this function bounces back and forth between positive and negative 1. And so this function never settles in on a particular, getting close to a particular y value. And so we would say that the limit as x approaches infinity of sine of x does not exist because we are not approaching a specific y value. Good. Okay, other questions or comments? Okay, so I gave this example as an example where a function crossed the horizontal asymptote infinitely many times just so that you don't walk out of here saying function can never cross a horizontal asymptote. Okay. Now let's go back and look at an example of a function that is slightly less complex. Let's take a look at the function y is equal to 1 over x cubed. Now if I draw a picture of this function, y equals 1 over x cubed, this function has two branches, one in the first quadrant, one in the third quadrant. And so based off of this picture that I've drawn, and you should check that this is what the function looks like by graphing it in your calculator. But when I look at this function, and I look at the limit as x approaches infinity of 1 over x cubed, I'm looking at what happens to the y value of my function as x gets really large. And what's happening here is that this y value, the graph here is getting closer and closer to the x-axis. So as x gets really big, the y values of my function are getting very, very tinier. And so our y values are going to 0. And so we would say that the limit as x approaches infinity of 1 over x cubed is equal to 0. Now, I can double check that, and I can make myself a table to confirm this. And so if I create a table of x values, if I start out, let's start out with x is equal to 10. If you plug in x equal to 10 into the function 1 over x cubed, what do you come up with? 1/1000? So 1 over 1,000, which is 0.001. Okay. All right, if we allow x to be equal to 1,000, well, now we've got 1 over 1,000 cubed. And so if I want to write that with a decimal value, how many zeros am I going to have before I write down the 1? 5? 6?
9, 27.
27?
I liked it.
9? All right, so try it out. I mean, try it in your calculator, see what you come up with.
10 to the negative 6.
What's the separate ones?
9. 10 to the negative 9. All right, so if I wanted to write that with my decimal, then I would take my 1, and I'd move the decimal over 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Micro.
And fill in all those places with zeros. So I'd end up having 8 zeros and then a 1. Now, x equals 1,000 is not very big. If I put in x equal to 1,000,000, well, now I have 1 over 1,000,000 cubed, which is, that denominator is pretty stinking huge. And my numerator is a 1. So if I take one item and I break it into millions and millions of pieces, each piece is extremely tiny. And so when I'm evaluating these numbers, as x gets really big, as x goes off to infinity, our y values are becoming extremely tiny. And so it turns out that this is going to happen anytime that we have 1 divided by x raised to any positive power. So in general, for n a positive integer, and in fact we can generalize this to any positive number, but we're going to go with positive integer for now. For n a positive integer, the limit as x approaches infinity of 1 over x to the n is equal to 0. So if we take the number 1 and we divide it into many, many, many pieces, each piece is very tiny. That's what this limit is telling us. And not only can we do that with positive infinity, but we can also do that with negative infinity. We can make a separate table here, and for this particular example, if our x values were negative 10, negative 1,000, negative 1,000,000, well, then this would be negative 0.001 and negative 0.0000001, and this would be negative lots of zeros and then a 1. And so our y values would still be approaching 0. And so this generalization over here, the limit as x approaches plus or minus infinity of 1 over x to the n is equal to 0. All right, now just that piece of knowledge right there is going to help us to work with these limits algebraically. And so let's take a look at a slightly more complicated example. Let's look at the limit as x approaches infinity of 3x squared minus 5x plus 2 over 4x squared plus 1. Okay, so our goal here is going to be to solve this limit algebraically. Now, when I look at this, what I see is, I see some highest powers. I see an x squared in the denominator. I also see an x squared in the numerator. And so in order for me to set this problem up so that I can use my knowledge that I've just written over on the board over here, what I'm going to do is I'm going to look at the highest power in the denominator. In this case, that highest power is the x squared term. And we're going to multiply the numerator and the denominator by 1 over that highest power, so 1 over x squared. So I've got the limit as x approaches infinity of 3x squared minus 5x plus 2 times 1 over x squared over 4x squared plus 1 times 1 over x squared. Now since I've done this to both the numerator and the denominator, it's like multiplying by 1. So I have not changed the value of my expression here. Okay, so check out what happens here now. This 1 over x squared, I'm going to distribute that to each term in my numerator. I'm going to do the same thing in my denominator. So So when I multiply 3x squared times 1 over x squared, those x squareds are going to cancel, and it's going to leave me with a 3. And when I multiply 1 over x squared times 5x, well, one of the x's is going to cancel, but one of the x's is going to remain in the denominator. So I'm going to have 5 over x. And my last term, I've got 2 times 1 over x squared, so that gives me plus 2 over x squared. Now in the denominator, I've got 1 over x squared times my first term, which is 4x squared. So those x squareds are going to cancel, and it's going to leave me with a 4. And then I have 1 over x squared. All right. Are there any questions about how I came up with these values? Not why I did it, but how I came up with these. Okay, so now the question is, why did I do that? And the reason that I did this is because when we work with limits, the thing about limits is that we can distribute a limit symbol as long as the limit in the numerator and the limit in the denominator exist, and as long as the limit in the denominator is not equal to 0. Now, at the beginning, if I tried to distribute this limit symbol, I'd have some pretty big stuff in the denominator. The limit of 4x squared as x gets really big, that's going to be big, and so that's going to be an infinite limit. It's not going to work for us. So we cannot distribute our limit symbol in the very beginning. But now that I've done this algebra trick, take a look at what's happening. If I look at my denominator, as x gets really big, this 4 stays as it is. The 1 over x squared gets really tiny. As x gets really big, 1 over x squared is going to 0. And in my numerator, the 3 remains, but as x gets really big, 5 divided by a really large number, well, that gets very tiny. That term goes to 0, as does 2 over x squared. And so when we take the limit of each term, which we are allowed to do as long as our limit's not equal to 0 for the entire denominator, which is not because of that 4 right there, we can take the limit of each term, and our final value here is 3/4. So algebraically, what's happening here is we performed an algebra trick, and what it did is it allowed our denominator to not be equal to 0 and also not be equal to infinity. And so we were allowed to distribute our limit symbol to each term. Most of the terms went to 0 and left us with 3/4. So what this says is, if you graph this function, 3x squared minus 5x plus 2 over 4x squared plus 1, you graph that on your calculator, and you watch what happens to the function. As x gets really, really big, the y value of our function is approaching y equals 3/4. And so we have a horizontal asymptote at y is equal to 3/4.
Is that with any highest power? Could you do x cubed or x to the 4th and do 1 over x cubed or 1 over x to the 4th?
So if I were to try to do 1 over x to the 4th on this one here, or you mean like if I had an x
Like
to the 4th?
if that were x to the 4th and let's say the top was just x squared like it is, do you still do 1 to the x to the 1 over x to the 4th?
Yes. So you always want to look at the denominator for that highest power, even if it mismatches from the numerator. And our next example, we're going to see y.
Okay.
Okay, so our horizontal asymptote is y is equal to 3/4. Now, something that is a good observation here is that, yeah, these highest powers are the same in the numerator and the denominator. And so, sort of conceptually, what's happening in this algebra here is that when x gets really big, this plus 2 on the top is negligible. Taking 3 times a million squared and then adding on 2, nobody cares about the plus 2. Okay, so that's negligible. And in fact, when you have an x squared, the x term itself becomes negligible once your x values are really large. So all of these lower power terms become completely negligible And in the denominator, this plus 1 becomes negligible. And so we end up focusing on the largest power in the numerator and the largest power in the denominator. And when those match up, when you have the same power in the numerator as in the denominator, then that's when you get a horizontal asymptote. That's when you have a function that levels off. Now, in a scenario where the power in the denominator is larger, then what's going to happen is a scenario similar to the 1 over x cubed, where the denominator is going to get really big, but the numerator is going to be negligibly small. And so you're going to have a horizontal asymptote of y equals 0. But let's look at an example where we have a higher power in the numerator. Okay, so let's take a look at the limit as x approaches infinity of x cubed minus 2x plus 3 over 5 minus 2x squared. All right, so when I look at this function that I have here without my limit symbol in front, some things I notice are that it's a rational function. And I notice that my highest power in the numerator is degree 3. So my numerator is degree 3. My denominator is a degree 2. My highest power is squared. So what I'm thinking here is that I'm expecting my overall function, my numerator is going to trump the denominator, since the power on top is larger. So this is my thought bubble on this, and hopefully when we do the algebra, we'll end up getting this same answer in the end. Okay, so when I look at this, I want to focus on my denominator, and my highest power in my denominator is squared. So when I multiply, I want to multiply by 1 over x squared, because that's my highest power in the denominator. And so we'll end up with the limit as x approaches infinity of x cubed minus 2x plus 3 times 1 over x squared. And in the denominator, we've got 5 minus 2x squared times 1 over x squared. Okay, so I want to distribute my 1 over x squared. So in my first term, I've got x cubed over x squared, which is going to leave us with an x. When I multiply 1 over x squared times 2x, it leaves me with a 2 in the numerator and an x in the denominator. And then I have plus 3 over x squared, 3 times 1 over x squared. Are there any questions about the algebra in the numerator? Distribution going on there. Okay. In our denominator, we've got 5 over x squared minus
2.
And this is going to be a 2. Okay, so we've now distributed 1 over x squared on the top and the bottom. So now I want to relook at my fraction here. So analyzing what's going to happen, well, I'm not so sure about this x, so I'm going to hold off on that one for a second. But this second term, 2 over x, as x gets really big, this guy goes to 0. And 3 over x squared, as x gets really big, that term also goes to 0, becomes negligible for large value of x's. And down here on the bottom, our 5 over x squared also goes to 0. And so what we're left with here is our limit as x approaches infinity of x over negative 2. We've got x minus 0 plus 0, and at the bottom we've got 0 minus 2. So now when I look at this expression right here, what happens to x over -2 as x gets really big? Yeah, the numerator, the x part, is getting very, very large, 1,000,000, 1,000,000,000, quadrillion. Now, we're cutting that in half, but it's still a large number, even though we're cutting that number in half. And so this x over 2 is going off to infinity, but because we have that negative sign in front, this entire expression is going off to negative infinity. So we would say that this limit is equal to negative infinity. Yes, Jen?
I can't remember. Does that mean it has an oblique asymptote, where you have one that's larger on the top than on the bottom?
So what's going to happen is that it depends on the difference in the powers. So on this particular example, if you were to graph this function, you would get a picture where, and I sketched this out ahead of time, so I'll draw it up here, but you should double check that this is what we have. We've got something that looks similar to this picture right here. And so as x gets really large, the y value of our function is approaching negative infinity. And in particular, the asymptote that we have is a diagonal line that looks like y equals -1/2 x. And that's what this is right here. That's telling you exactly what your asymptote is. Now, if you have like x squared over -2, then the sort of outlying features of this graph would look more like a parabola. Whereas here, the outlying features look like a line. Okay, so when our limit is equal to positive or negative infinity, then we say that we have no horizontal asymptote. There is an oblique asymptote, but here we're just focusing on a horizontal one.
Okay.
Okay, so before I ask if you have any questions, there's a question that I'm hoping some of you are thinking, and if you're not, then I don't want to be sad that none of you are thinking this. So I'm just going to blurt out this question. And this question is, well, why did we multiply by the highest power in the denominator? And the answer to that is, in particular, in this example, if I had tried multiplying by 1 over x cubed rather than 1 over x squared, in the numerator, we'd be fine. We'd have a 1, and then that second term would go to 0, and the third term would go to 0. In the denominator, though, we'd have 5. Our denominator would look like 5 over x cubed minus 2 over x. And so our entire denominator would be going to 0, and that's an issue. We don't want that to happen. Okay, we do not want our denominator to go to 0. So it's important to focus on the denominator for the opposite that's going on. Well,
wouldn't it still kind of give you the same answer, because if you have a 0 in the denominator, you said it kind of implies infinity, doesn't it?
So if we end up with a 0 down in the bottom and a numeric value on the top, which in this case we would have end up with a 1 on the top, the issue there is that this actually doesn't tell us that we're going off to negative infinity. We lost out on the positive versus negative infinity part of it.
Okay.
And so that's where it's important to make sure that you don't lose this part on the bottom.
Okay.
All right. So conceptually, when I see this, I see a higher power in the numerator than in the denominator. So I know that my numerator is going to trump. My function is going to go off to positive or negative infinity. Which way it goes, well, to figure out positive versus negative, I need to be a little bit careful with my algebra in the middle. All right, questions or comments on that? Limit that infinity.
So just so I'm clear,
Yes.
for when you're canceling out the two, like in the numerator and the denominator
Yes.
to get 0, whenever we see that, do we just automatically assume that it's doing that, or do we have to work that out to show it?
So precisely what we're using is this guy right over here.
Okay, all right,
So it's not really an assumption, but it's using that knowledge.
okay.